All right, so in this video, we're going to just continue looking at some examples dealing with polar area. And in this one, we're going to be finding the area common to both of those curves. You'll notice these are both going to be circles. This is going to be a cosine circle, so along the x-axis with a diameter of 2, circle along the y-axis with diameter of 2 as well. So let me go ahead and sketch that in here. I've got my 0, my pi over 2. Here's going to be the sine circle, and then here's going to be the cosine circle. And we're going to be looking into the common area, so that's going to be this part right here. Okay, that's going to be the region now that we're going to find the area of. Okay, so when we talk about, again, sweeping through this, if we sweep through it, we'll start here, looks like at 0, and we'll continue to sweep through. Now, as I continue to sweep through, I want you to pay close attention to something. Notice I'm always going to start here at the pole, but as I sweep through, for example, this guy's going to come out and touch this circle right here. But as I now continue around, as I come out, this is going to be touching this circle. So we're actually going to be changing our function somewhere through the process. And so that's going to tell us that we need two separate integrals in which then we would add up. So our first one might look something like this. Our area would be the integral, and I would have my 1/2 r squared d theta. And so to get this thing started, let's say I start here and I move out. It looks to be that when I hit my intersection point right here, that's going to be where I change over from this circle to this circle. So I'll go ahead and I'll start with my 1/2 this circle, which would be my sine circle. So that's going to be 2 sine theta quantity squared d theta plus the other side, which would be a 1/2 to cosine theta squared d theta. So as I continue past this now, my lines would come out and be touching this circle. That would be our cosine circle. So 1/2 to cosine squared d theta. All right, so now let's talk about where to start and end on these bounds. Well, for the sine circle, it's pretty clear that I would start here at 0. I would start at 0 and I would continue around up until I got to this point of intersection, and then I would stop, and then I would pick back up again here on my cosine curve all the way back down. And so let's go ahead and study now where that point of intersection is going to be. So to find the point of intersection, we're going to take the two things and we're going to set them equal to one another. So 2 cosine theta equals 2 sine theta, which says tangent of theta equals 1, which says theta equals pi over 4. So I'm going to go from 0 all the way around then to pi over 4. And I'm going to have to pick back up at pi over 4 and then continue all the way back around until I got to that pi over 2. And that together, the sum of those things together should give me the area that you see right here. Okay? Now, this is another one where you could use symmetry. I could very easily say my final answer is just going to be the 2 times the integral, let's say 0 to pi over 4, 1/2 to sine theta squared d theta. You would get the same answer there as both. I did think it was important in this one, though, to show you exactly how that changes over so that you can apply it then to other ones where you might not be able to use the symmetry like we could here. All right, so for our next one, we're going to take a look at finding the polar area inside this guy, which is another cardioid, and then to the right of this, which happens to be a line. So if I sketch this up here now, my cardioid is going to look something like this. Once again, it's a cosine cardioid. So we know that it's going to be along the x, or horizontal, if you will. So 0 and pi over 2. With it being plus, it's going to be in that direction. And I also know now that I've got my line in here. That's going to be vertical line if you convert that back into rectangular coordinates. All right, so we want to find the area now. inside the cardioid and to the right of the line. So inside the cardioid and to the right of the line would be this guy right here. So again, I'm going to always use symmetry when I can. And so my focus now is going to be on this region right here. I'm going to kind of shade that in, the borders at least around in blue. So that's what I'm going to find. Now, to do so, my area, of course, is going to be needing to be doubled because I'm only going to figure out half. So I'll go ahead and I'll set up the integral. And I'm going to have now, once again, a big minus a little. If I use the cardioid as my function, that's going to give me everything leading out to it. And I don't want everything, okay? I'm going to take the big, which would be the cardioid itself, minus the little, which would be this. So the big, all of that, minus the little, which is this, okay? So the cardioid itself, we're going to have a 1/2 the cardioid, 2 plus 2 cosine theta squared d theta, minus the little, which would be the line itself. So 3/2 secant theta squared d theta. Okay, so far just the big minus the little. Now we need to figure out where we're going to start and where we're going to finish on our sweeper. Well, it's pretty clear that we're going to have to start here at 0, and then that's going to continue up and around. So we're going to start at 0 on both of these, and then we're going to have to stop whenever we hit this right here. Well, much like the last one, that's just going to be a point of intersection. So if I take the 2 plus 2 cosine theta and set it equal to the 3/2 secant theta, I can now solve this for my theta. And so moving some things around and considering the secant is 1 over cosine, this is going to give me 4 cosine squared theta plus 4 cosine theta plus 3 equals 0. Excuse me, that's a minus 3 when I subtract it over, equals 0. And this is going to factor into 2 cosine theta minus 1 and 2 cosine theta plus 3. This guy here says cosine theta equals negative 3/2, which can't happen. We know that cosine is always bounded between 1 and negative 1. But this guy says that cosine theta is going to be 1/2. So if cosine theta is 1/2, that tells us that theta is going to be pi over 3. And that kind of makes sense with what our picture looks like. This angle right here, from there down, should be about our pi over 3. So I'll go ahead and circle back and drop this in. I've got my pi over 3 here, and once again, pi over 3 here. So that should be the computation now to give us the area of inside the cardioid but outside the line. So we have a big minus the little. The big gave us all of that, minus the little, which was just that, and our sweeper goes from 0 all the way around then to pi over 3. Okay, so for our last example, we're going to take a look at a looped limacon, and we're going to find the area between the loops. Now, because of how our sweeper works, and because we have this interior loop that is going to play a big part of this, I found it to be important that I went ahead and I graphed it like we talked about in an earlier video, where I have my theta axis, my r axis. I graphed this guy right here, which is my sine curve, shifted up 1 unit. It's going to be reflected about the x-axis, and it's going to have an amplitude of 2. So in graphing this, I've come up with this graph here where I've actually color-coded it to be helpful here in just a moment, but I've also labeled my points here, the 5 points, 1, 2, 3, 4, 5, but in fact they're labeled r comma theta to help us better understand how this is going to put our polar graph together. So let me go ahead and do this now. So I'll go ahead and put this graph together, 0 to pi over 2. Our first point here is going to be the point 1, 0, which the point 1, 0 is going to be right over here. So there's 1, 0. And it's going to then move to negative 1 pi over 2. So negative 1 and then pi over 2 would put us right down here. So negative 1 and in the positive direction, pi over 2. So I'll go ahead and I'll put that there. And if you'll notice, this is where I cross over that theta axis. So as I travel from this point to this point, I'm going to have to go through the pole. So from here to here, going through the pole is going to be me coming around like this through and connecting. All right, and again, I'm doing this in black to make it easier to understand here in a minute. So there's that. All right, so from there, this is currently where I am, -1 pi over 2. I'm going to need to go from there and travel to 1 pi. So 1 pi would be right over here. And notice that's in green, so I'm going to be consistent with that, keeping it in green. And just like the last one, as I travel from that point to this point, as I travel from this point to this point, I'm going through the theta axis, which means I have to go through the pole. So if I travel correctly, I'm going to go through the pole like this and back around. And then for the yellow portion, I'm going to go to 3 pi over 2. So 3 would be out here, 3 pi over 2 would take me around. Maybe I'll extend this axis here a little bit more. And that was going to be in yellow. So that's going to now connect there. And then finally, my red, which takes me then back to 2 pi, which is right here. So now I'm coming in like this. All right, so the color coding that you see up here is the same as the color coding down here. And we're trying to find the area between the loops. So this area right here, we don't want this, just the area between the loops right there. So to do this, you can probably imagine I am going to go ahead and use symmetry once again. The symmetry that I'm going to use is going to be a big minus a little, and we'll just focus on one of the sides. So let me go ahead and get this set up, at least to a certain extent. All right, so my area is going to be, using symmetry, something and then minus something else. And then we'll close it up there. Now, it's going to be a big part of the problem is going to be figuring out where I want to start this. Let's say that I'm going to focus on this area right here, which I am, okay? This is going to be the area of my big, but then I'm going to subtract out my little right here, okay? So area of the big is going to be this whole thing here, minus this little piece, okay? And I've doubled it to take into consideration this side here. So to get the big part, I'm going to have to start where the green intersects the pole. That's this guy right here. So I need to figure out what that is. Then I'm going to continue with that all the way until where the yellow ends. Then I'm going to subtract out where the black intersects the pole all the way down to where the black ends. Okay? So I'm going to need to figure out this guy here and this guy here. Well, to do that, that's of course where your r is equal to 0. So if I take the original 1 minus 2 sine theta and I set r equal to 0, this is going to allow me now to find what our theta values are. And so theta here would be a pi over 6 and a 5 pi over 6. All right, so this guy right here, that's going to be our pi over 6, and this guy right here is going to be our 5 pi over 6. So, as I mentioned before, for the big, I'm going to start where the green hits. The green hits right there at 5 pi over 6. So 5 pi over 6, and that's going to travel then around all the way until where the yellow ends, which would be right here, which would be a 3 pi over 2. So that's going to be a 3 pi over 2. And then I'm going to subtract out the little part that I don't want. That's going to start where the black intersects, so pi over 6. So that'll be a pi over 6 right there. And then it's going to travel all the way around to where the black ends. The black ends then at pi over 2. So I've got my pi over 2 right there. So those are the bounds, and that's generally the hard part as you've seen in earlier examples. So now we'll just go ahead and drop in the actual functions. We're going to have our 1/2, our r would be 1 minus 2 sine theta squared d theta, and then the same exact thing over here. So when it comes to these types of problems, we can't just always take it at face value that the numbers that we're going to need are the numbers that you see from the original plotting. Instead, by looking at it in color codes like we have here, you can start to see where if you need to take a specific piece of the graph, you can now see where to take it and where it relates back to the original. So I strongly recommend these types of graphs for these types of problems. It's going to keep organization a whole lot better in the big picture.